So when we started the semester, one of the first topics that we covered was this idea of understanding the differences between different types of data, categorical data or nominal, as we might call it, numerical or scalar data, certain special kinds of data like that, like discrete numerical data, categorical data that has a certain order that's inherent to it, the ordinal data, and so on and so forth, and combining those different kinds of data when we want to do statistical analysis. So, for instance, if we want to compare the mean age of a group of people in one location to a mean group of people in another location, we would sample that first location, find the average age, compare it to the average age of the people in the other location. For instance, compare the means of those two groups, the average ages of those two groups. We're dealing with two groups, Group A and Group B. That's a categorical variable, right? Nominal or categorical variable. Could be a country, France and England. Could be a borough, Brooklyn and Queens, for instance. Could be male and female, right? Those are all categorical or nominal variables. The actual thing that we're comparing are means, which are native to numerical variables. We find averages of numerical variables like age, so an average age. So there we're combining nominal data and categorical data, and we use a specific test for that, a t-test. Well, each one of these comparisons of data are going to include specific tests that we're going to work with on these things. And I'm gonna blow this up so we can see it a little bit better. Okay, so if we look at this chart gives us kind of an idea of where we're looking, how we're using these statistical tests. So for instance, if we want descriptive statistics, we want to describe the nature of a group. So let's say that you choose to do the analysis that's involving who's likely to get a flu shot based on whether they have insurance, based on their age, based on many other factors, and so on and so forth. One of the first things you might want to expound on in your presentation is a description of what your population looks like. So, for instance, in the community health survey, the population involves people from 18 years old and older. There are no people under 18 in that survey. So that's significant. There's no children involved in that survey at all. So you might want to bring that up. You might want to show us the distribution of the ages, maybe a bar chart or something like that. You might want to show us what percentage of people are male and female and so on and so forth. Even though that's not directly what you're addressing with your statistical test, you might want to give us a little bit of backward, maybe the ethnic distribution of the population that you're looking at, just as background information. Descriptive statistics or background information on the population that you're working with, so we get a feel of who these people are, who these subjects are. Okay, and then you might want to go on and then choose certain variables that you're interested in. Now, in the case where you're comparing one group to another group, where it's a numerical variable. Okay, let's say where are we in here? Let's see. We're comparing two groups, right? So not paired groups. In other words, not the same person tested before and after an intervention, right? But we're looking at two separate groups, like the description I just gave you, the mean age before and after. That would be a t-test. And we know there's several different kinds of t-tests that we can do. We can single sample t-test, we can do independent sample t-test, and we can also do that paired sample t-test, right? So we have t-tests that we use to compare the means of a numerical variable in two groups. Well, the problem with that, and that is that, well, what if our categorical variable, instead of being male and female, Brooklyn and Queens, let's say it involves all five boroughs, Brooklyn, Queens, the Bronx, Staten Island. What did I leave out? Manhattan, right? Let's say it involves all five boroughs. We want to compare the average ages of people living in those five boroughs. Well, now we have five groups that we want to compare the means of, not two. Well, if we do a t-test, we know we can only compare two groups at a time. the average for Bronx and Brooklyn, the average for Bronx and Queens, and so on and so forth. And we'd have to repeat that test many times. Each time we repeat it, we have the potential for rejecting the null hypothesis when we shouldn't. In other words, a type A or a type 1 error. Okay, so we don't want to do that. We use another test. We use analysis of variance to determine whether there is a difference in the means of those three groups, or those five groups, or whether all five of those groups have the same mean. That would be our null hypothesis, right? They all have the same mean. Our alternative hypothesis is that at least two of them have different means, right? Maybe more than two, but at least two of them have different means. That's what analysis of variance will tell us. And then after we've determined that, and if we've determined that, then we can go on and do post hoc tests and analysis of variance to determine which of the means are different. Okay, so that's what we do with analysis of variance. Well, how about if we only are dealing with categorical variables? In other words, situations where we want to compare whether males or females are more likely to, let's see, whether males or females are more likely to be left-handed, right? So you have two categorical variables, male or female, gender, in other words, variable male or female only has two values, and whether or not a person is left-handed or not. Left-handed, yes, left-handed, no, right? So that would be simply two categorical variables. Well, we would form a table, a crosstab or a contingency table, which would organize that data so we could see the rate at which people, the males are right or left-handed, and the rate at which females are left-handed. We can compare the two of those two. In that case, we would use chi-square. Do I have it here? Quantify patient's correlation. That's one sample t-test. Don't see it here. Oh, I guess I left that one out. Okay, so you would use chi-square there. Oops, let me play this again. You would use chi-square in that case. And, oh, here we go. If we're dealing with categorical variables, we would use chi-square or odds ratio and relative risk. If it's a 2x2 table, if it's more than a 2x2 table, we would just use chi-square. We can't use relative risk or odds ratio directly because we need a 2x2 table unless we modify the data, the way the data is organized. For instance, the one I just mentioned, I could have a situation where I could have asked you to compare the left-handedness for or handedness for males and females. And in the rows, I could have had male and female, but in the columns, I could have had left-handed, right-handed, or I could have had that they're neither left-handed. They have no preference for left-handedness or right-handedness, right? So I could have three categories, three values for that variable handedness, and two for the male or female, right? Male or female or gender, right? And that would be a 2x3 table, right? In which case, it'd be a little bit difficult to do an odds ratio there. So you could certainly still do chi-square. Would change your critical value for chi-square, your degrees of freedom, but you could do chi-square for that to see if there's an association or not. Okay, and then finally, we also sometimes deal with numerical variables, and we want to compare two numerical variables. This is relatively new material for us, right? So in that case, we're, for instance, trying to see whether or not a person's grade point average, for instance, I have a data file that I just stuck up here that I'm going to be using to demonstrate this. Let's say we're interested in knowing whether or not a person's score on the graduate record exams before they came into school correlates or has an association with their grade point average once they're in school. Okay, so in other words, both of those are numerical variables. As a person has as people have higher grade point averages, do they also GREs? Does that translate into higher grade point averages as well? Or maybe taking that test doesn't really convert that well into predicting how well people do in their studies. So we might want to take a look at that. That's a numerical variable. And a numerical variable, we're going to take a look at how that works as well. Okay, so any questions so far? Did I forget something? Is there anything there I left out that's important, do you think, so far? That was a real quick summary of some of the things that we've been going through up to this point. Okay, so I'm going to start with, I'm going to work a little bit backwards. I'm going to start with the newest materials that we covered. In other words, correlation and regression. Okay, so I'm going to open up a data file. Let's see if I can find where I put it now. Okay, so here we go. So I'm going to open this data file, correlation, regression. And you're going to see it probably when we get to class again, or when you see the newer material that'll be posted this week. It might look a bit differently. I'll open this up in SPSS so we can take a look at it. Okay, so what do we have here? We have 4 variables: admit, GREs, grade point average, and ranking. Okay, so what do we have here? We have a nominal variable, admit or not admit, in other words, did they get into school or not, GREs, grade point averages, and we have rank, right? In other words, the ranking of those students, which is an ordinal variable. We have a categorical variable, which is ordinal. We have numerical variable, and we have a categorical variable. Okay, so I'm going to take a quicker look over here, and you'll notice that it's labeled scalar and scalar for these 2 numerical variables, and the others are labeled nominal, right, for whether the student was admitted based on their GREs and grade point averages. I guess that this would be in college, their undergraduate grade point average and the GREs that they took. So let's say that we wanted to see whether there's an association between a person's grade point GRE score and their college grade point average, their undergraduate grade point average. Well, seems like you would think so, right? Seems like that might be a logical conclusion, that people that have a higher grade point average in college would probably have a higher GRE score as well. But we don't know that for sure, right? Let's test that. Let's test that assumption. So we're going to start out with the assumption that there's no association between a person's GRE scores and their grade point average. And we're going to try and prove that there is. In other words, we want to reject that assumption and prove our alternative hypothesis that there is an association between grade point average and GRE. Okay, so let's see how I might do that. Okay, so I'm going to go up here and I'm going to say, first of all, let's go up here and take a look at this data. I'm going to say, let's take a look at how this data looks graphically. So I'm going to go up to create a graph, which is a scatter plot. Legacy dialog, scatter plot. What this is going to do, I'm going to choose simple scatter plot. What this is going to do is it's going to set up a graph with an X and a Y axis, where the X axis is going to be a student's grade point average, and the Y axis is going to be a student's GRE score. So in this case, my independent variable is going to be grade point average, and my dependent variable is going to be graduate record exam score. So we're basically saying here, can we predict our GRE score from our grade point average? Is there an association there? Well, first thing we might want to see if there's a correlation, if they're associated at all. In that case, it doesn't matter which one you call the X and the Y. But once we go a little further, we want to re-examine this again to see if there's a real association where one variable actually influences the other variable, not that they just coincidentally go up together, but that there's a real association and one could have some influence on causing the other to change. Well, when we get to that, it's going to be important which one we choose to put in the x-axis, the independent variable or predictor variable, and which one we put into the y-axis, the predicted or the result variable, the dependent variable, depending on the grade point average, for instance. Okay, so let's take a look at this. I'm going to click OK. Let's see what our graph looks like. Okay, very interesting here. So a lot of scores here, right? But one of the things I notice that it kind of blocks off here because the maximum score is 800 on this particular test. But it sure does look like there is an upward movement here that as students, as a grade point average goes higher, they tend to also have higher grade point GRE scores as well. I can double click on this and ask it to give me a best fit line. And I think that's going to be, here we are. Okay, there we go. There's a best fit line for this, right? There's a lot of scattering around here. Doesn't look like it's all that predictive, but it does look like there is an association there. So I think this might be worth pursuing. Okay, so the scatter plot, each one of these points represents an individual here. In other words, that point represents a person who had a grade point average of 3.3, let's say, and had a GRE score of 400. And this person over here had a grade point average of 3.5 and a GRE score of maybe 650 or something like that. Okay, so each one of these is defined on an XY scale by their grade point average and their GRE score. Okay, so let's see if there is. Let's start with our assumption that there is no association. Let's test that assumption. Let's see if there is at least a correlation, an association between these two. So I'm going to go up to Analyze. I'm going to go to Correlate, Bivariate, because it's two variables, right? Grade point average and GRE. Notice I need to put two variables in there before it will say OK. Okay, now it says OK. I'm going to ask it to go ahead and do this Pearson's correlation coefficient. That's what we know is that R value. I'm going to say OK. Okay, and look, it goes ahead and calculates the Pearson's correlation coefficient for me. And notice that it says that this correlation is not zero. That R, remember our assumption is there's no association, no correlation between these two values. Well, that's the same thing as R. That correlation coefficient is equal to zero. Well, in this case, notice it says no, it's different. It's 0.384, that R value, right? So that R value is 0.384. How certain are we that it's not that value by chance, that it's not different from zero by chance? Well, we're less than 5% chance of being wrong if we reject the null hypothesis, that there's no correlation between these two values, right? So this significance tells us that we can reject the null hypothesis, accept the alternative that there is an association between the two. How strong an association is that? Well, remember the way that we determined this was this R value, it could have a value from -1 through 0 up to +1. 0 means that there's no association at all. 1 means that there's a perfect association, very strong or perfect association. You can predict exactly how much one's going to be from what the other one is. Some perfect association between the two of them. As one goes up, the other one goes up in lockstep, right? Normally won't see that. What you will see is that there's some scattering or some level of predictability from one to the other, right? So in this case, that value is 0.384. Well, remember, 0 to 1 was the range, right? So 0.384 tells us that there's an association. It's not the strongest association in the world, but there is some association. And we're going to be taking a look at how significant or how important that association is. Notice that this is a positive number, not negative 0.384. Remember, it could be from -1 to +1. It's not negative 3.84. What does that tell us? That tells us that as the value for the x-axis goes up, the value on the y-axis goes up as well. So in other words, as the student's grade point average goes up, it's likely that he'll get a higher, along with that, he'll get a higher GRE score as well. So it's a positive correlation, upward. Had we found that this was negative, it would be predicting that as the student's grade point average went up, the GRE score went down. Not likely to occur, but if that was the case, it would have been a negative correlation. And the slope of that line that we looked at before would have been downwards instead of upwards, this best fit line. Okay, so let's take this a step further now. we're going to go to Analyze, and we're going to do a process called regression. We're going to analyze how predictable one variable is based on the other variable, the value of the other variable. So, of course, is only for numerical variables, goes along with correlation. So I'm going to go into regression. I'm going to go into linear. Okay, and in this case, notice I still have to put two values in there, two numerical variables in here. But in this case, I have to put in which one I think is the predictor value and which one is predicted based on that value. So I'm going to say a person's grade point average is going to predict his GRE performance. Makes sense because he's getting his grade point. He's going to school and getting his grade point average. In his last year, he's taking his exam. So I'm going to say that this is the predictor for that rather than the other way around. Okay, so I'm going to go ahead and I'm going to say okay. And let's see what we wind up with here. Okay, so first of all, we wind up is an analysis of variance, an analysis of whether we can say that there is an association between these two variables. In other words, again, our null hypothesis is that there is no association, right? So it's going to do a significance test, which we did before. This is the source of that significance test that we looked at before, 0.000, less than 5% chance of being wrong if we reject that null hypothesis and say that there is an association between these two variables, the alternative hypothesis. Let's take a look at the values that it found for R. R, that Pearson's correlation coefficient, is equal to 0.384. Okay, that's what we found before for the correlation. That makes sense, right? And that's based on how far all those values were from a line, a best fit line, right? And then it also calculated something called R squared. And in fact, R squared is just simply 0.384 squared. So it's 0.148, about 0.15. What this tells us is that we have a statistically significant association, so we can reject the null hypothesis that R is equal to 0, right? And say and accept the alternative hypothesis that it's not equal to 0. In other words, there is a correlation or association between these two variables. Number one, but it also tells us that the change in the value of the person's grade point average accounts for 15%, around 15% of the variability in their GRE score. Aha! Now, so what does that mean to us? That means that there's a certain amount of predictability here, and that this is a grade point average, this is their GREs, but only 15% of the variability. In other words, how different it is based on the person's grade point average. So 85% of the variability is based on other factors, right, of which there could be many. So that's a little disappointing, but it is significant, right? There is a significant, statistically significant, and also, in terms of like the actual score, significant impact of a person's grade point average on their GRE score, but there are many other things that can be involved in this as well. Okay, so the other table that we get from analysis of variance is a coefficients table. Okay, and you'll notice here it says that the coefficients are a constant and then some unstandardized coefficient for GPA, for grade point average. Remember, this is the predictor variable. Okay, now the grade point average has a predictor value, has a coefficient of 116 or 117 almost, and the constant coefficient is 192. These represent values for the formula of the straight line that we see here. So in other words, the formula of this straight line is y, the value for the grade point average, GRE score, is equal to 117, actually 116.639, 117 times the person's grade point average plus 192, which is the y-intercept, the place where the y-axis, notice 200, the y-axis, the line crosses the y-axis at a value of 192 as it happens here. Okay, so this is, we can predict the formula of this line is the grade point average y is equal to the slope of the line, which is 116 or 116.6, right? Times the grade point times x, the grade point average, plus the y-intercept for that line. So we now have a formula that we can use to actually predict what the y value is. In other words, what a person's GRE score might be based on what their grade point average is. So is a perfect predictor? It's certainly not as far from a perfect predictor, as you can see here by the scatter here, right? But now we have a tool where if I know a student going into the GREs, his grade point average is 3.8, I have a method, a formula here that I can use to calculate what I think his GRE score might be. Now, there is a way for you to actually go here and say analyze and go here to regression, to linear regression, okay, and go into save and click off unstandardized predicted values and unstandardized residuals. I'm going to click continue and click OK. What that does, it actually takes this formula that we read from here, and it goes to our data view, and it creates two new variables. So, for instance, for this person, number 5, their grade point average was 2.93. Our formula predicted that it actually figures this out. You could do this manually by hand. Our formula tells it that the predicted value for that person's, based on the formula, for that person's GRE score is 534. In fact, we know that person had a score of 520. So the difference between these two is the error that was built into our formula. And instead of error, they call it the residual. So this is the residual difference between the two of these. In other words, the real value was 14 points lower than what we had predicted. And actually did this for every one of these people, not just for new ones that you might put in there. Can you say which coefficients is again for? Oh, yes, absolutely. Absolutely. Okay, I'm going to go back there. Fortunately, since we're recording, you can always go back there and do it again. So here we go. Okay, so I don't have my graphics tablet hooked up here, but I'm going to scratch it out with my mouse. Okay, let me narrow this down so it's a little easier to work with on my screen. Okay. Okay, so okay, I'm gonna go to this table right here, coefficients. Okay, so the formula is gonna be y is equal to mx plus b. That's the way a mathematician usually writes a formula for a straight line, where this is the y-intercept and this is the slope of the line. Right. So, but most of the time, statisticians will kind of, their notation might be something like this. Might be y is equal to ax plus b, where a is the slope of the line and b is the y-intercept. Really doesn't matter, because whether you use that or that, because you're really going to wind up with the same formula, because in reality what we want here is GRE, y is the GRE score, equals a. Well, what is a? A is the slope, which is 116.6, 116.6 times the grade point average. Remember, that's a 0.6, plus the y-intercept, which is 192.3. Right? So if you want to know what the GRE would be for a person who had a grade point average of 3.0, it would be equal to 116.6 times 3.0 plus 192.3. Right, so that I'm not going to work that out right now, but you could actually calculate what that grade point average would be in that case. That makes sense, out right? Okay, does that clarify that for you? This number is the slope. This number is the y-intercept. Good. Okay. I'll see if I, can find. I'm sure I have somewhere some other stuff I'll be posting this week for in the Wednesday session, for the Wednesday session, that summarizes, the regression formulas and so on. Okay, so let me go backwards now a little bit to chi-square. And I'm going to do something a little bit unusual. I just want to review chi-square, odds ratio, and analysis of variance, because that's a couple of people asked questions about that on the discussions board. And I always encourage you guys, please go to the discussions board and put your questions there, because then I can address them for everybody at the same time, because I guarantee you, if you're having problems with it, other people are having problems with it too. Let me, by the way, I noticed every once in a while my school of public health email stops downloading, and I miss a bunch of emails. And I noticed I've been away for a week, and I noticed that while I was away, and even for a little bit of the week before that, while I was away, it stopped downloading, and I missed a bunch of emails. So I'm going to be catching up on them. It might take me a couple of days, but I'll be catching up on every one of them at some point. Okay, so let's take a look at that. This is the full data set for the community health survey, right? There were 209 different questions that were asked in the community health survey. We actually have if I can find it back here, we actually have the code book for this. Okay, I'm going to open it up. Okay, let me get rid of the PDF file behind it. Okay, so let me see if I can't find a couple of categorical variables that look interesting to us. Let's see. Here's one. Have you ever been told by a doctor or other health professional that you have asthma, that you have had asthma? Okay, and that is a yes or a no question. That's ever asthma is the variable, and yes and one means yes, two means no. For have you ever been told that you've had asthma? Okay, so I'm going to look for maybe another categorical variable, which might be associated with asthma. Okay, that's these dietary questions. Smoker. Okay. Here's one. Every day. Okay. Every day. The question is, do you smoke every day versus some days? Okay. So let's see if we can't compare people who smoke every day versus people who smoke some days with regard to whether or not they've ever been diagnosed with asthma. Okay, so I'm going to open up SPSS. I'm going to open up this data file in SPSS, which I've already done. And, I'm going to, in order to find these variable names, I'm going to say data. Let's see. Sort cases. And I'm going to ask it to sort the cases by the name. Oops, nope, that's not what I want. Data. Sort variables. Okay, I'm going to ask it to sort it by name so they're alphabetical. Easier for me to find them. Okay, so here we go. So the first one I'm looking for is ever asthma. Okay, let's see, ever asthma. What was the other one that I was looking for? Ever asthma and every day, I think, right? Here's ever asthma. And where's every day? It's gonna be after that. Here's every day. I'm gonna narrow this down. So they only have those two variables here for me to play with. Make it a little easier for me to deal with this. I just picked those two categorical variables out very quickly, just so I'd have two categorical variables to work with. There's kind of a funny variable that every day, because it's smokers, but smokers who smoke every day versus casual smokers who might smoke every once in a while. I'm going to organize this. I'm thinking that smoking every day is a risk, is going to be something that's going to make it more likely that you're going to be diagnosed with asthma. I could be wrong. We're going to take a look at that. There's a reason why I could be wrong, right? But we'll see. So I'm just going to fill in these values here. I think it was 0. Was it 0? Let's see. Cancel. Let's see. Nope, that's not what I want. Where is it? So for every day, 1 was yes and 2 was no. Okay, values. 1 is smoke every day, and 2 is smoke occasionally. Okay, and what about ever asthma? I think 1 was yes and 2 was no. But we'll go back. Let's go back here and take a look for it. I'll do a search. Ever asthma. And this kind of thing you could do on your own when you're considering 1 is yes, 2 is no. When you're considering which variables do you want to choose to work with when you're examining your options for your project. 2 is let's see, 1 was yes, yes. Say asthma, and 2 is no asthma. Okay, so I've coded these so we can see what they look like now. There we go. Okay. A lot of people are not smokers, so they're not even considered here, right? Okay, so I'm going to go ahead and I'm going to organize this data. I'm going to say analyze. Now, we need to organize this into a 2 by 2, 2 by 3, whatever kind of table, 2 categorical variables. We go into descriptive statistics. We go into crosstabs, because we're building a crosstab or contingency table. In the row, I'm going to put the exposure, which is their smoking status. In the columns, I'm going to put the outcome, whether or not they have asthma. And let's see, in statistics, I'm not going to fill that in yet. I just want to take a look at the cells first. I'm going to put observed values. I'm going to put percentages by rows as well. And I'll click OK. Let's see how many people fit these categories. Okay, here we go. We have, let's see, out of 7,400, out of 8,698 people, 7,450 of them are not smokers at all, so they don't show up here. So we have 1,248 people that fit into these two categories. Let's see, smoke every day, we had 760 people. Smoke occasionally, we had 488 people. Out of the 760 people, 120 people smoked. The percentage, the rate of smoking, the risk or rate of smoking in that group is 16%. Among the smoke occasionally, the rate of smoking is 17.2%. Wow, people who smoke occasionally are more likely to have been diagnosed with asthma than people who smoke all the time, smoke every day. That seems like a surprising result. Do you have any idea why that might be true? Does that seem like a reasonable result? Oh, yeah, gender would have been good too. I hadn't thought about that, but yeah. But what do you think of that result? That you're more likely to have been diagnosed with asthma if you're an occasional smoker versus, hey, they don't smoke every day because they have asthma. Obviously, right? Seems obvious once you see that result, right? But in the beginning, you say to yourself, well, gee, smoking associated with asthma and so on and so forth. But yeah, after they've been diagnosed, then it's likely they may be not likely to smoke anymore. Just like if we were looking at diabetic or not diabetic, and we asked them whether they drank sugary beverages, right? Well, diabetics probably less likely to drink sugary beverages than other people because they know they've been diagnosed with something that should tell them not to drink that stuff, right? So yeah, pretty interesting. But now let's go ahead and analyze this data and see if the differences here are due to chance or if there is a real difference, a real significant statistical difference between the rate of smoking, people asthma smoking, people asthma smoking occasionally, right? So let's take a look at this. I'm going to go up here to analyze. Now, again, descriptive statistics crosstabs, right? Because we have two categorical variables, we're going to do a chi-square, and we're going to do a odds ratio and relative risk. I'll click off risk, and then I'll click OK. So our null hypothesis here is there's no association between asthma and whether or not you smoke every day or occasionally, right? So let's see what our, and the alternative hypothesis is that there is an association between those two. Let's see what our result looks like. Here's our table again. So our Pearson's chi-square value is 0.085. That looks like a pretty low number to me. Remember, they would, with the 2x2 tape, was the critical value was 3.84. That's not very encouraging, right? So when I look at that, I say, that doesn't look so very encouraging to me. I look at that and I say to myself, okay, it's 0.085. It's less than the critical value for 1 degree of freedom. In other words, a 2x2 table, which is degrees of freedom is rows minus 1, 2 rows minus 1 is 1, 2 columns minus 1 is 1, 1 times 1 is 1, meaning degrees of freedom is 1, and the critical value for that is 3.84. So if I look at this, so I said, boy, this doesn't look like I can reject the null hypothesis. And then when you go over here to the significance or the p-value, the probability of being wrong if you reject the null hypothesis, it's, or in other words, you could phrase it another way, probability you get this extreme a value for Pearson's chi-square when when you can't reject the null hypothesis, and the null hypothesis is true. Well, this would come up 77% of the time, so if the null hypothesis is true. So it's not less than 5%. We need less than 5% chance of being wrong, of creating a type 1 error before we reject the null hypothesis. So we fail to reject the null hypothesis. We can also look at the odds ratio. Remember, we looked at the odds and the odds ratio. We noticed that people who smoke every day have lower risk of having been diagnosed with asthma. Well, let's see. Odds ratio for smokers smoking every day is 0.956. Well, no difference would be 1. So our null hypothesis here is that the relative odds ratio and relative risk are equal to 1. Our alternative hypothesis is that the odds ratio and relative risk are not equal to 1. So look, it's close to 1, but it's less. But is that enough less that I can reject that null hypothesis that the relative risk is equal, that the odds ratio is equal to 1? Well, in fact, if you look at my 95% confidence interval, we're not really sure it's that value. That's the value we got for this group of people. But for the whole population, we're 95% sure it's between 0.7 and 1.2. Well, that means that we can't be 95% sure that it's not 1. It could be 1. It's almost right in the middle of that range, right? So that tells us we failed to reject the null hypothesis. And this is the odds ratio. This would be the equivalent of 16.6% divided by 17.2%, right? And that also has a significance which is not less than 0.05, far from less than 0.05. So we fail to reject the null hypothesis there as well, because the confidence interval, well, here it is over here, but yeah, the confidence interval includes 1. So that would be the way we would handle categorical variables. Now, the other thing I wanted to mention was analysis of variance. And I wonder if I have a data set that's handy that I can get to quickly. Let's see. Square, relative risk. No. Let's go back into this data set. Let's stick with ever asthma. Oh, I just closed it, didn't I? I just erased all the other data sets. I wonder what what's the numerical. We don't have that many numerical data sets. We got age, I think. Okay. Let me find something interesting here. Household, that's categorical variable. I want something numerical. Income. Let's see if there's an income variable in here. Any others here? See if we can find one that's not. No, not going to be able to have an age. I think there is an age group, age. Here's sex. Right. Let me grab that one while I'm here. I guess it won't let me copy this. Do this. And sex. Let me find something numerical here. I think it could be in demographics. Let's go back here to have a lot of age stuff here. Age group. Let's see. Age. Interesting. I know there were some numerical variables here. Mental, physical, demographics. Health insurance, diabetes, mental health, demographic. Can be in demographics. 27. Three. 28. Let's see categories. More annoying. What did I ask it here somewhere? Where is it? Here's another one that might come in handy here. I'll take this also. So remember it, demographics. By years. I'll tell you what, I got another way of doing this. Yeah, I got these two. I'm gonna look at my variables. If I had time to do it, I would really go through these data set a little bit more carefully. Let me reopen this data set, this SPSS data set. Desktop. Let's reopen this. Okay, let's see if I can't find numerical variable. Oh, here we go. This is age right here. Demog1 is the person's age. I just happen to remember that. Okay, so I am going to go here. So I am going to get rid of all these up to Demog1. I'm doing this because it's just easier for me to work with this stuff. I don't have to be distracted by all the rest of these variables I'm not using. Demog1, and the other one I'm interested in is ethnicity and sex, which Demog 135R. Demog 135. Oh, before I do anything else, I am going to sort this data, sort by variables, sort by name. Okay. Okay, good. Get this out of the way. Okay, 135R. Oh, I think I needed to undo that. Unfortunately, Demod 1 is in here. Yep, I don't want to do that one. Clear. And then I want to go from that one to Demod 135. R. And then I'm going to want, I have those two, and I want sex also. Let's see. Here we go. Okay. Good. I'm going to rid of the rest of these here. I don't need them right now. There's a way to filter these instead of deleting them, but just a little bit easier for me to do that at least. Okay, so what do I have here? I have a variable, which includes gender. Okay, if I look at the data here, you can see, oh, I screwed this up. What did I do? Demog 1. How did I get that wrong? Uh-oh. What did I do here? Okay, Demog 1 I want. Down to Demog 135. You know, it's not select. Oh, I'm in the wrong key here. Here we go. Bear with me just another second. Okay, let me check what I have left here now. Yes, I have the ones I want now. And now I will get rid of the rest of these. Okay, and just I want to check one more thing here on our variable on our code book, and that is, where's our code book go? Well, it doesn't matter anyway. I'm going to go in here, and I'm going to say that 1 is male. I don't remember which one it is, but I'm going to say 1 is male and 2 is female. And okay, and you'll notice that Demog 137R, what that is to ask them to identify their best group that represents their age and heritage. And there's a number of different groups that are located in that file, a number of different ethnicities. So we have a categorical variable with 2 values. We have a categorical variable with more than 2 values. And we have a numerical variable. Let's say I wanted to see in this sample, which represents population New York, adult population New York, is the average age for males greater than the average age for females? I'm comparing the averages of 2 groups. So what test do I use? I use Analyze, compare means, independent samples t-test. If I were comparing a single sample like males against a certain age I knew, 35, let's say, we'll use a single sample t-test. If I were comparing the age before and after some intervention, I might use the paired sample t-test and so on. Compare, I'm going to say independent samples t-test. I'm going to say the test variable, in other words, I'm finding the mean of is the age, which is a numerical variable. The grouping variable is the gender. Now, because I'm only doing two cases, two possible variable values, 1 and 2, male and female, I have to tell SPSS what the values are that it might be dealing with 1 and 2. I'm going to click OK. The output table would open up. Our null hypothesis is that the mean age of males is equal to the mean age of females. Our alternative hypothesis is that mu, population of males, is not equal to the mean age for females. Males is not equal to the mean age for females. Okay, and let's see what happens here. Well, my significance for my quality of variances is 0.411, right, which is not less than 0.05. So I stick with the top row. And you can also see the standard deviations are very close. So we're assuming equal variances. So if I go across the top here, we can see the t-score is negative 3.592. That's pretty high for a t-score. This is the degrees of freedom. The probability of being wrong if we reject the null hypothesis is less than 5%. So males, there's a difference in the average age for males and females. And that difference is statistically significant. We're more than 95% certain, less than 5% chance of being wrong, that there is a difference in the average age for males and females. Okay, that's the statistical result. Is it clinically significant? I guess a year and a half difference in average age. That means a lot that there's a lot of older females than there are males in New York City. So yeah, it might be clinically significant in terms of the public health finding. If it was only 48.41 to 48.51, and it was statistically significant, this was less than 0.05, we'd say we reject the null hypothesis, the means are the same, but then we might look back here and we might say to ourselves, yeah, but clinically it doesn't make that much difference. So clinically it's not significant, but statistically it might be. In other words, we could prove we could prove within a reasonable amount of doubt that the two populations have different means. Well, how about if we have more than two values in our categorical variable, like our other variable, which was different Asian ethnic groups? Let's try that. Analyze this. Compare means. We're still comparing the means of these ages of these different groups, right? Except now, I can't use independent samples t-test because there's more than two values for the ethnic groups, right? So I have to go down here to analysis of variance. So I'm going to put my age into the dependence list, and instead of putting the sex, I'm going to put the ethnic groups into the factor box, right? I'm going to go ahead and tell it to go ahead and run that. It's going to run a one-way analysis of variance. It's going to compare the variability within the groups and outside of the groups, and it's going to find that our F value is 7.349. Now, what is our null hypothesis? Well, there are 7 different groups of ethnicities in this population. It doesn't display them here. There are 7 different groups, right? The degrees of freedom was 6. 7 different groups that are identified here. And our null hypothesis is that there is no difference in the average age of these 7 ethnic groups. And our alternative hypothesis is that there is a difference in the average age of these groups. In other words, mu1 equals mu2 equals mu3 equals mu4, so on and so forth, for each one of the substituting 1, 2, 3, the name of the ethnic group. And then our alternative hypothesis is that at least 2 of these means are different. But not all of them, maybe not all of them, perhaps all of them, maybe 3 of them, maybe 2 of them, but at least 2 of them are different. So now that I get a result that says that I can reject my null hypothesis and say at least 2 of these groups have a significant average age, significant difference in the average age, Now I can go back and say analyze, compare means, one-way analysis of variance, and this time I can go in here and click post hoc and ask it to do what is a relatively conservative post hoc test after the fact, after we've shown that we can reject the null hypothesis post hoc test. I'm going to click continue. I'm going to click OK. And this Tukey post hoc test will be run, and it will compare each one of the ethnic groups to each one of the other ethnic groups. So if we look over here, it gives us the significance of the difference between the means. Between 1 and 3, it's not significant. We can't reject the null hypothesis. But we can reject the null hypothesis for a difference in the means between 1 and 2, between 1 and 4, between 1 and 7. Okay, and then it does every permutation. You'll see it will repeat occasionally. 2 and 1, we already did 2 and 1 up here. It did 2 and 1 again. So you can go through all these and figure out which ones you can reject the null hypothesis on and which ones you can't reject the null hypothesis for. Okay, so analysis variance, you're comparing the means of more than 2 groups. T-test, you're comparing the means of 2 groups. Chi-square odds ratio, you're looking for an association between categorical variables. And correlation and regression, you're looking for an association between 2 numerical variables. Okay, so I hope that quick run through of this helps out a bit. Again, post questions so I can address them in the discussions forum, because that's really the best mechanism for me to get to everybody that might have these questions. Remember, there's 60 people in the 60 students in the online section, so it's hard for me to get answer questions individually as detailed as detailed a manner as I can when I answer fewer questions for a bigger group. I try and answer every question, obviously, but although obviously this week I've been away, so I've fallen behind a little bit. So and I had my email problems, but I try and answer every question I can individually. But I can really give more time to it if I answer questions that the group poses that I know. Again, I can't tell you. I've done this for a while. I can't tell you that. I can't tell you I can't express how strongly that I've noticed that when one person might bring a question up, and then suddenly a lot of people realize that, well, I've been thinking the same thing. I really wanted to answer that same question. Right? So really is effective to use in this kind of course. Really is effective to use that in a way that gives us the biggest advantage in terms of communicating information.